Thank you so much, sir, for a nice introduction. It's a pleasure to be here. So let me start by sharing my screen. Uh, Please let me know if it's visible. So. Okay, thanks a lot. So, good afternoon, everyone. So, I will start with advanced graph partitioning, and I'll talk about how do we partition a graph into subgraphs, and why do we do it. I am going to discuss this. So, let's start. So these are the contents that I would be discussing over here. So I am going to discuss a few partitioning algorithms and what do they do, why are they required. So I'm going to discuss about it, and I'll start with introducing with a few applications why it is required and what are the challenges, similarity measures. So how do we do it, why do we do it, and I'm going to cover a few subset of algorithms related to this topic. So first of all, these are the first of all in graphs. Suppose I'm going to discuss about two types of graphs. First is the bipartite graph, and another one is web graph. So what is a bipartite graph? We all know what is a bipartite graph. Bipartite graph is a graph where we have two sets of vertices, and in one set all the edges are from one set to another set. So if there is edge, so one end of that edge is in one set and another end of edge is in the second set. That's the bipartite graph. Now where do we use this graph? Suppose in an organization there are multiple products and customers are purchasing those products. So how can we so we can say, okay, there are customers and there are products. Now what do we want to do is we want to cluster a subset of customers buying similar kind of products. For example, customer number 1 and 2 are purchasing every similar kind of products every month. Okay, so what if suppose customer number 1 purchase a third product which is customer number 2 has not produced. So what we will do is we will suggest customer number 2. So it's called product recommendation. So the owner can recommend the second product based on their buying patterns, right? So here the similarity between the groups, customer groups which are purchasing similar kind of products is identified. So where this bipartite graphs comes into action, we want to cluster out the similar kind of customers that have similar kind of purchasing patterns. This would help us in product recommendation, identifying the buying patterns, and so many other things. Okay, so this is one of the application of graph partitioning. Another application is web engine. Now you all know that whenever we suppose we are doing a Google search, we will click on something, we click on next page, we go on next page, and we keep on going like this. So the idea, what I want to say over here is we might have infinite number of connections. So can you think of the graph, web graph, or what is a web graph? I'm talking about web graph. So web graph is nothing, it's just a connection of nodes and edges. But what kind of nodes? So consists of every web page as a node, and when I'm clicking on some button in the web page and I'm going to next page, so next page is another node. Okay, so I can represent my clicks via a web graph. So if I click on next, so I am moving from first page, web page A, to web page B. So there are two vertices A and B, and there is an edge. So edge is everywhere where I am clicking and going to the next web page. So that's called a web graph. So identifying web graph, how would it help? So identifying a web graph would help in identifying web pages, detecting web spams, and disclosing, finding out which communities, suppose I'm engineer, and all the engineers would search similar kind of web pages. If someone is doctor, so doctors would search similar kind of web pages, right? So web graphs are useful in clustering or identifying the partitions where similar kind of web clicks are done. This is also called click-through information. Click-through information means which pages one by one I'm clicking on and going to next web page. So that is a click-through information. Okay, so this kind of information is also one of the application where the graphs are used, and you can see, there are many applications of graph these days. Also, you can also imagine image pixel as a graph. Image is suppose 50 cross 50 image, 50 pixels in left to right, and you can also imagine it as a graph. Why? Because all the neighborhood pixels behave similarly. For example, if one pixel is black, there are high chances that its neighborhood pixels would be black. Okay, so that's also a graph. So everything around you can be represented as a graph. Next application I would see is social networks. Now this is very I don't know if there's someone of my age and your age and even younger generation, I know. So everybody knows about social network. So what a social network is, it's a connection, interconnection between people. So what we want to achieve via this is, it's not necessary. So in online world we want to connect with people in an online way. So those networks, basically that's a social structure between individuals, between people and between organizations, and the links are the interdependencies between the vertices. So I am vertices, so every person or every organization is a vertex in a social network. And what are the edges? If I am connected to 5 web pages in my Facebook or my Instagram, so all those 5 web pages that I am connected to are my edges. Okay, so this is how a network is represented in a social network or maybe social networking websites these days. So how it is helpful, if you search some web pages, you get recommendation of those web pages. If you search for some shopping websites on Facebook or Instagram or any other social network, you will find recommendation for similar kind of web pages. So those recommendation, promoting products, promoting sales, those kinds of things, these are all the applications where the graph partitioning is used. So I hope this I'm able to explain the several applications. Next is challenges. Now we all know about machine learning, we all know about data mining, data science, we all know how does that works. How does that works is, I have an object and I have a data sample and I have attributes associated with that object. Suppose I have I have a simple if I am talking about the data set of images, okay, or if I am talking about a data set of text, maybe sentences. So or if I am talking about weather data. So in a weather data, if you pick out one sample, you are having multiple attributes like temperature and time and date and so many other attributes. But in graph that is not the case. You don't have attributes associated with any object. Object is a vertex and relationship between the vertices is the edges. So there are no attributes associated with the object. So challenge in the graph partitioning or graph clustering is that you cannot apply simple maybe k-means clustering or maybe density based clustering. You cannot do it directly because you don't have features, you don't have set of attributes associated with data sample or object or vertex, because you have vertex and edges over here, right? So how do we do it? So the how can we measure the similarity between two objects on a graph? So how can we do it? Two objects means if it's another data set, that is two data samples, two data points, right? But in a graph you have two vertex. So how do you identify the similarity between the two vertex? Okay, first is, this is one of the primary challenge in the social network or maybe a graph partitioning problem, Then another challenge is how can we design the clustering models and methods that are effective on graph and network data. Like we want to design particular algorithms that belong to particular graph kind of data set, right? They should be able to classify or cluster the graphs kind of data set or data objects in the graph, not the simple numerical data where you have time series data. No, that's not the case, right? So these are the several challenges. So I'm going to discuss the few solutions, although there are many advanced clustering algorithms or partitioning algorithms that can divide or produce the clustering among the graph kind of data set. So I'm going to discuss a few of them. So first is, let's discuss about the similarity measures. And why are we discussing this is, I want to know that in a graph having suppose 5 vertex, what are the chances that vertex A is similar to vertex C. Okay, so what I want to do is I want to identify the similarity between 2 points of vertex in my data set or in my network. Okay, so first thing is I can simply do the geodesic distance, and second is a SimRank. So there are 2 types of similarity measures I'm going to discuss. Like in normal data set, what you have Euclidean distance. And how does Euclidean distance is computed? X minus y square, right? Root of x minus y square. You have Minkowski, you have cosine similarity, and you have Jacquard similarity in case of a sparse data set. Okay, so different similarity measures are there. So I'm going to discuss similarity measures for graph kind of data set. Okay, so first is geodesic distance. What is the geodesic distance? So geodesic distance between 2 vertex is the length in terms of the number of edges of the shortest path between the vertex. For example, if A and C are the 2 vertices and there are they are connected by 2 edges, and from another path they are connected by 3 edges. So what is the shortest distance between A and C? So this is the simplest similarity measure between vertex A and C. What is the distance between A and C? I would say if it's larger, then they are dissimilar. If the 2 are nearer, then they are similar. They work in a similar way. Okay, actually this is not the case, but we will see later on. But this is the simplest distance or similarity between the nodes or between the vertices. Okay, so for 2 vertices that are not connected in a graph, geodesic distance is defined as infinite. Suppose I have one graph and another graph, and there is no distance between the nodes in the 2 graphs, then I would say the distance is infinite between the 2 vertices. Okay, so next, there are several other notions that we use to that utilize this geodesic distance. One is eccentricity. Eccentricity is one of the primary, basic measure that is used. And what is it? The largest geodesic distance between V and any other vertex U. Okay, U that does not belongs to V. Okay, so largest geodesic distance. Geodesic distance was shortest distance between A and B or any 2 nodes. And what is eccentricity? It is the largest distance between any node. Okay, so I hope you are getting the idea behind this. Let's see an example. So if I talk about A and C, so the distance between A and C is 2. Okay, and what is the eccentricity? Eccentricity is also 2 because at the max it can reach from A to any node is 2. Okay, so eccentricity is also 2. Similarly, if I calculate from D to C, shortest distances this 1, 2 and 3. 1 to 3, from D to A to B and B to C. So that is shortest path or geodesic distance. So geodesic distance is 3 for D to C. And if I calculate the eccentricity of node D, that means from node D at the max it can go to 3 distance. Eccentricity is at the max 3. That means From D to E distance is 1, from D to A distance is 1, from D to B distance is 2, and from D to C distance is you can say it's also 3, and you can also go via E. So D, E, A, B, C. So that is 4. So out of 3 and 4, which one will you take? You will take the shortest one, which is geodesic distance. So distance between D and C would be 3. Okay. So maximum eccentricity for D would be 3. Okay. Similarly, I hope the concept is clear. So this is how we calculate the eccentricity of every node. Next is the radius. Radius is the minimum eccentricity, and diameter is the maximum eccentricity of all the vertices. So out of you will calculate the maximum eccentricity of all the vertices in the graph, and then you will say, okay, diameter is 3 for this graph. Okay. Peripheral vertex is a vertex that achieves a diameter. Example, vertices C and E are the peripheral vertices. Okay. So those vertices that achieves a diameter, that means eccentricity 3. So you can see that D and E, C, D and E all are having eccentricity 3. So we will say that these 3 are the peripheral vertices with maximum diameter. Okay, maximum eccentricity. Okay, another method. So first method is geodesic distance, this one. And what is the disadvantage is, suppose I have two nodes A and B, and I have two nodes C and D. Okay, so A and B, distance from A and B is 1, and distance from C to D is also 1. So can I say that A is similar to C? Geodesic distance says so. Yes, it is. But no, that is not the case. Okay, because A might have some more neighbors. A can have 5 neighbors, and C can have hundreds of neighbors. So C is more complex than A, right? So geodesic distance does not gives the weightage to the neighborhood of the vertex. If I have 5 neighbors, I am in a less complex network. If I have 5,000 connections with me, so I am in a more complex network, right? So this similarity measure does not, gives a great idea about the similarity. So we use SimRank also. So SimRank is another method. So it takes into account the structural context similarity based on the similarity of its neighbors. Okay, so how does this work is, in a directed graph, G is equals to VE, you have in neighborhood and out neighborhood. In neighborhood means incoming edges, and out neighborhood means number of outgoing edges. So basically for every node, I will calculate the similarity rank based on number of nodes I am connected to, number of incoming edges and number of outgoing edges. So incoming edges are for U and incoming edges for V. Okay, and similarity between X and Y is the number of incoming edges, and C is a constant. C is a constant over here, which says that as you keep on increasing the distance, so it will constant will reduce its value. Okay, so its range is generally between 0 and 1. Value of C is between 0 and 1. And initially how you would compute SimRank? So for one node, so how am I similar to myself? So that is 1. So similarity is 1. And so if U equals to V, then similarity is 1. Okay. And then for second node, I will compute the similarity from myself to the my nearest neighbors, then to second neighbors, and to third neighbors, and so on. Okay. Then another first is structural context similarity. Similarity based on the context, based on the neighborhood. Okay. And second is a similarity based on the random walk. What is random walk? Random walk is you walk from A to X via B, C, D, E, F. So that's a random walk. You take some random path. Okay. So probability that distance between A and X is connected, and how much they are strongly connected. So that is defined by this formula, which is expected meeting probability sigma PT CLT, and PT is probability and C is over here. If you see LT is the length of the walk. If I am traveling via 5 nodes, so length is 5, because if distance between A and B length is 1, if A, B, C, 3 nodes length is 2, and so on. So length and then multiplication of length and probability. Okay, so that is how you calculate the similarity based on the random walk. So these are the two methods. So this second method where we describe, either use structural context or we use a random walk, this is a very popular method. Okay, generally this describes better the graph similarity or vertex similarity in a graph. Okay, object similarity in a graph as well. So let's move on to the algorithm, partitioning algorithm, and how do we do it. Okay, so the intuition behind the clustering or the partitioning is to find the clusters in a graph. Imagine the cutting of a graph into two pieces. Basically, what do you want to do? You want to cluster the graph or partition a graph, and what do you want to do is it should be divided in such a way that all the nodes in A are similar to each other in first partition, and all the nodes in B are similar to each other in the second partition. I'm sorry, someone is asking something. Okay, so okay, so so I was discussing about the discussion how to partition graph into two clusters, and why do we want to do it. It's a simple clustering way. And what do we do in clustering? We divide the data into two groups, and first groups, all the points in the first group should be similar to each other but dissimilar to all the points in the second group. And similarly, in the second group, all the points in the second group are similar to each other, but the points in that group are dissimilar with the second point group with the points in the second group. Okay, so this is one basically what do we call, it's a simple clustering. So in case of graphs, what do we want to do is we want to find a cut such that it would divide the graph into two subgraphs. Okay, and what kind of cuts are good? How do we decide that? If I have a complex graph, how do I decide where to cut the graph from? So the algorithm is, I want to find out the best cut that divides my graph into two subgraphs. Okay, so there are polynomial time algorithms to compute minimum cuts of a graph. Okay, so graph clustering, let's see. So what do we want to do is we want to find out the sparsest cut. So the cut set of the cut is the set of edges, and S and T are the two partitions. So basically this is the cut set, minimum cut 1, and this is the minimum cut 2. You can see there are two cuts in the graph as shown in the right hand side. So there are two cuts. So out of these two cuts, which one is better? You will visually you can say that cut number 2, C2, this cut is better, right? So this cut is better than this cut, right? So I want to cut in C2. This one is better and this one is wrong. Okay, why is it so? Because cut C2 is partitioning the graph into a better way, right? And I want to identify this cut, sparsest cut. Okay, this is also called a sparsest cut. Now what is a sparsest? Sparsity. Sparsity formula is this. This is the sparsity. And how do we calculate the sparsity? One thing what we want to do in dividing this graph is, first thing we want to divide this graph into clusters. Okay, now in such a way that this cut should be having minimum number of edges. So it was having one edge and two edge, but this cut was having only one edge. So how I can say that second cut is better and first cut is not better? Because I want to have minimum number of edges in the cut, right? But I am selecting this one. Why I am selecting this one? Because it is making my graph balance. I do not want to have like one node in another one partition and all in the second partition, right? I don't want to do that. I want to divide make a balance in the cut such that the number of edges in the cut are very less, as well as it should divide in a balance. Okay, and how do we maintain that balance? Using this formula. So S is the number of nodes in this S graph and T is the number of nodes in the T graph, and I want to find out the minimum balance. If you calculate for this graph, so one size of the cut is for this graph, if I calculate for this graph, it would be 1 divided by minimum of S and minimum of T, minimum of this whole and minimum of this one. So this would be 1, right? And if I say that the size of the cut in this case, second case, so that would be the this would be 2 divided by this. Okay, so sparsest cut is sparsest if its sparsity is not greater than that of any other cut. Okay, we want to find out good sparsity. Okay, second is the modularity. So second is a modularity, and how do we calculate it? Using the degree, number of nodes it's connected to, and the edges between the vertices in the ith cluster, that is Li. Okay, so this is the formula for modularity. Modularity of a clustering is a difference between the fraction of all the edges that fall into individual clusters and the fraction that would do so if the graph vertices were randomly connected. So basically we want to maximize the modularity. If our graph have maximum modularity, then we will say this is a best cut. Okay. Now, challenges of finding a good cut. Okay, so there are several problems. It is a very NP hard problem, because in a graph there can be infinite number of cuts, right? There can be infinite. Now this is only having 10 or 15 nodes. In real life, if you see a social network, you have millions and billions of connections. Okay, they're around the world. So how do you divide? So this is a NP hard problem, right? And there is a trade-off between efficiency and scalability. As you keep on increasing the size of graph, it's very difficult to divide. Second problem is, we are talking about simplest graph. This is simplest graph. If graph are very complicated, like they have cycles, they have infinite loops, they have a looping problem, they have disconnected components, right? So that is a complicated graph, and in those graphs this algorithm would not work pretty well, would not work. Okay. Third is high dimensionality. Dimensionality means many vertices. So it can have an infinite number of vertices. So in that case also, this will not be it will not be very easy to find a good cut. Sparsity. A large graph is often sparse, meaning each vertex on average connects to only a small number of other vertices. So similarity matrix from the large sparse graph can also be very sparse. So again, sparsity problem is also there. So I'm going to discuss two approaches for graph clustering. First approach is the generic clustering approach, and second is the scan algorithm. Scan is a specific algorithm. This will work only for graphs. And first approach is generic clustering, where I have discussed the similarity measures, and you can use those similarity measures to and another spectral clustering method to use for the graph. Like you can use it for normal data set as well, and you can use it for graph as well. So in spectral clustering, what do is we just we find out the affinity matrix, similarity between basically each and every node, and then what we will do is we find out k eigenvectors and we form a matrix over here, and then we find out k eigenvectors, and all these eigenvectors will transform the data into a new data space, and then we will find out optimal clustering. We can apply k-means or any other simple clustering method, any clustering method, and then we can segregate the data set easily. We just want to transform it into a lower dimension and in a new dimensional space, and then what we will do is we apply simple k-mean clustering or something, and then we can project the data into back, like transform and then inverse transform to the original data, and then we will find the optimal clustering. Another method is scan algorithms. This scan algorithm works similar to dbScan. I hope you all know about density based clustering algorithm. So in dbScan is for normal data points, where we have so we have density based clustering, which means there is a core point, right? There is a inside point, right? And you have epsilon distance. So all the points inside a core point within the epsilon distance are called core points. This is called the edge point, and then you have some noise points, right? So from this you again calculate nearby neighbors and then nearby neighbors and so on. So this is based on density, right? So this is how this scan also works. So this structuring clustering algorithm for networks is also kind of works similarly. And how do you find out how many clusters, what is the size, what is the best partitioning? So these things are we are going to see. And given simply information of whose associates with whom, could one identify clusters of individuals with common interests or special relationships. So this algorithm is used in identifying the similarity between networks. So you can apply this algorithm very easily. You just have to specify a few you have to set the value for epsilon, minimum number of points. You have to set the value of mu, and a few constants are there, and you have to set these values, and then you can simply apply this algorithm. It will work for graph. Okay, and how does this work? So there are several notions about this. So there are, first of all, let's understand the social network model. We have clicks, hubs and outliers. Outliers are the points that resides at the margin of the society. Individuals who are hubs know many people in the different group but belong to none. Okay, I'm connected to 3 clusters, but I am not belonging to any of the clusters. So I am a hub. And click is a social group. Click is the those individuals which are in a cluster, okay, in a social group. These are all called the click. So there are 3 types of points. And in a scan algorithm, what do we want to do is we want to identify which point is a click, which point is a hub, and which point is a outlier. If you can see in the graph, this point is a hub. It does not belong to this one, and neither it belongs to this one. Okay, so you start from here and you keep on assigning whether it's a hub or it's a which point, it's a click, it's a hub, or it's an outlier. Okay, you start from here, then you can say all these points are click, and then all these points are click, and so on. Okay, so you keep on calculating and increasing your size of the cluster, and then you can say, okay, these are. So once you find this as click and this as click, you have 2 sub networks, 2 clusters. Okay, this is the idea behind a scan. So that's the overall idea I have told you. And this is psi v as the intermediate neighborhood of vertex. So the formula for this is structural similarity. Basically, how do we find out the similarity between these two? Is the number of u and number of v in the nearby neighborhood of u and v. Basically, for every node, if I want to calculate between u and v, so I will see the number of nodes in the neighborhood. Okay, then epsilon neighborhood is whatever value neighborhood I am getting, whatever value in the neighborhood of v I am getting, it should be greater than 3 or maybe 4 or 5. So this epsilon value is a constant, like in dbScan. In dbScan also exact same thing happens. If distance is greater than some epsilon neighborhood points are 5, from me 5 nodes are connected, I would say I am lying inside the cluster. If I have only 1 neighborhood point, I am not lying inside the cluster. Okay, this is the idea. So epsilon value you have to set, again mu value you have to set to decide whether it's a neighborhood point or it's a core point. Okay, this is how, and then you find out whether these u and v are structurally connected or not. Okay, so you start from here, you say, okay, it's an outlier, it does not belong to any cluster, and then you you check for this 9 and then 8 and then 12 and then 10 and so on. You start and you say, okay, 6 point is a hub, it does not belong to any cluster, but it's a bridge to many clusters. So this is all about the scan clustering. So there are many algorithms. I think that's all from my side. If you have any questions, you can ask. So thanks a lot.